Hello students, once again welcome to my YouTube channel Physics with Dr. Sanjay Bhargav. I once again request you to view and subscribe my channel @Sanjay Bhargav 6807. In the first video lecture, we provided information about charges and its properties, Coulomb's law, then properties of the electrostatic force and the concept of dielectric constant. In today's video, we would try to understand the concept of continuous charge distribution, then how to calculate the force between multiple charges and compare the properties between electrostatic force and the gravitational force. For comparison of the properties between electrostatic force and the gravitational force, we select an electron-proton system. Now, the two are separated by a distance r. One can always calculate electrostatic force between electron and proton. It would be given by the Coulomb's law, which says force is equal to K, charge on the electron, charge on the proton upon square of the distance. Similarly, the gravitational force Fg can be calculated as G, mass of electron, mass of proton, and r square. Now, what are we supposed to do? We are supposed to find out what are the similarities and what are the differences between gravitational force and the electrostatic force. When it comes to similarities, you can see from the two equations, both forces obey inverse square law. Electrical force proportional to 1 upon r square, gravitational force proportional to 1 upon r square. Now, electrostatic force and gravitational force, since they obey inverse square law, both the forces are supposed to be central and conservative. When it comes to central force assumption, that means the direction of the force must always be along the line joining the center of either two charges or the center of two masses. When it comes to the concept of conservative force, then a force is said to be conservative when the work done along the closed path is equal to 0 or the work done depends only on initial and final positions. Both forces can operate in vacuum. Now, when it comes to differences, let us see. Then we find that gravitational force is always attractive, while the electrostatic force, it can be attractive or repulsive depending upon the polarity of charges. In gravitational force equation, we have universal gravitational constant, that was G. So, which is having the same value at all points in the universe. So we say gravitational force is a medium independent force. That means does not depend upon the nature of the medium. But when it comes to electrostatic force, then we have K as 1 upon 4 pi epsilon 0. If the value of epsilon changes as per the medium, then the force also changes. So we say electrostatic force depends on the nature of the medium, and that dependence is through permittivity. Then electrostatic force is very strong as compared to the gravitational force. Now the question is, how strong is the electrostatic force with respect to the gravitational force? So for electron-proton system, the gravitational force we said was given by this equation, electrical force given by this equation. I can always calculate the ratio Fe upon Fg, which would be equal to K, charge on the electron, charge on the proton, gravitational constant, mass of the electron, mass of the proton. The value of electrostatic constant is 9 into 10 raised to power 9. Charge on the electron is 1.6 into 10 raised to power minus 19. Charge on the proton is 1.6 into 10 raised to power minus 19. The value of the gravitational constant is 6.67 into 10 raised to power minus 11. Mass of the electron is 9.1 into 10 raised to power minus 31 kilogram. Mass of the proton is 1.6 into 10 raised to power minus 27 kilogram. A simple calculation would give the figure as nearly 2.4 into 10 raised to power 39. That means I can say the electrical force is nearly 10 raised to power 39 times the gravitational force. Here we can have different types of system. We can have a electron system, then we can have a electron proton system, and we can have a proton proton system. In case of electron system, this ratio comes out as 10 raised to power 42. For electron proton system, the ratio is 10 raised to power 39, and for proton proton, the ratio is 10 raised to power 36. Now, we already studied Coulomb's law in our first lecture. Just to check our understanding, let us face the question: divide a charge capital Q such that the force between the two parts is a maximum. How to approach? This charge Q, let it be divided into small q, and the remaining charge then would be equal to Q minus Q. How to calculate force? Through the Coulomb's law, that is KQ into Q minus Q upon R square. For any maxima and minima, the first derivative has to be 0. So we can calculate df by dq and make it 0. K upon R square is constant, so d by dq of q into capital Q minus Q square would be equal to 0, which gives me the differentiation as q minus twice q must be equal to 0, or q must be equal to q by 2. So when will the force between the divided charge be maximum? When the charges are divided equally into 2. So we write force is maximum when charge is divided into 2 equal parts. What was the utility of the Coulomb's law? It was able to calculate force between two stationary point charges. Now what happens when we have multiple charges? We can have a system of charge ranging from Q1, Q2 to Qn. Then we need to calculate what would be the force on a given charge. Now we consider a system of n charges: Q1, Q2, Q3 and Qn. The distance of Q1 from the origin R1, Q2 origin say distance R2, and for the nth charge the distance is Rn. We need to calculate force on the test charge Q0. That means the charge placed at the origin. And Q0 would experience a force due to presence of Q1, Q2, Q3, Qn. And what does the superposition principle say? According to superposition principle, the total force acting on the test charge Q0 that was placed at the origin due to system of charges is equal to the vector sum of forces exerted by the individual charges on Q0. So what is the force on the test charge? That is F. Q0 is experiencing a force due to Q1, Q0 is experiencing a force due to Q2, Q3 and then Qn. Now, will there be a force between Q1 and Q2? Naturally, both the charges are present, there must be a force. But while using this superposition principle, we neglect the force between individual pair of charges. Why? Because in the first lecture, we already have proved that sum of internal forces acting on a system of charge is 0, and we proved F12 plus F21 was 0. Now let us utilize Coulomb's law to calculate Q0 F Q0 Q1. It would be K Q0 Q1 upon R1 chi square, K Q0 experiencing a force due to Q2 upon R2 chi square, Q0 experiencing a force due to Qn upon Rn chi square. Here Q0 is constant. K is also common, so I can write Q1 upon R1 chi square, direction given by R1 cap, Q2 upon R2 chi square, direction given by R2 ka cap, Qn given upon Rn chi square, the direction given by Rn ka cap. Just the entire things can be written with the help of summation as F is equal to Q0 summation I is equal to 1 to n K Qi upon Ri chi square Ri cap. So what does this equation provide? This equation provides the equation for the resultant force on the given test charge Q0 placed at the origin. Now question is, how to utilize this superposition principle. For that, we pick up an example. Here we have a square of side A. The square is A, B, C, D, and 4 equal charges are placed at the points A, B, C, and D. What are we required? We are required to calculate force on charge Q placed at C. Now, this charge is going to experience force due to charge at A, charge at B, and charge at C. The direction of the force on C due to B is this way along the line joining. So this gives me FCB. Force on C due to charge at D would be in this direction, and similarly force on C due to A would be along the diagonal. First, let us calculate the magnitude of the three forces. So I can calculate force on charge at C due to charge at D. So FCD is equal to KQQ upon A square. Both the charges are equal. That would be KQ square upon A square. Similarly, I can calculate force on C due to charge at B. Again, the distance is A. So it would be KQ square upon A square. Then I need to calculate what would be the force on charge C due to charge placed at point A, which is diagonally opposite to the point C. So diagonal, the length is root 2A. So KQQ upon root 2A ka whole square. So that gives me KQ square upon 2A square. The resultant force on charge C due to charges at B and D can be calculated, and for that FC B and D would be equal to FCD ka square, FCB ka square, twice FCD, FCB cos 90. Just see, the angle between the two forces is 90. Let us go back to the figure. So here the angle between the two forces is 90, right? And that is what makes cos 90 as 0. So we are left over with KQ ka square upon A square and KQ ka square upon A square, which gives me root 2 KQ square upon A square. Now the question is, what is the direction of the resultant force? So once again, go to the figure. To calculate the direction of the resultant, let's calculate this angle alpha. So tangent alpha would be perpendicular upon base FCD upon FCB. So let us go back. It would be tangent alpha would be equal to FCD upon FCB. Both the forces are equal. So tangent alpha is 1, which is tangent 45. So alpha is pi by 4. So what is the direction of the resultant force? Along the diagonal. So total force would be now the sum of the two forces acting along the diagonal only, and that is FCA and force on C due to B and D. Write the values of it: KQ upon KQ square upon 2A square, root 2 KQ square upon A square, and the total gives me resultant force as KQ square upon 2A square to root 2 plus 1. So that is how we calculate the magnitude of the resultant force and the direction of the resultant force. The direction of the resultant force is along the diagonal. That is from, I can say, figure from A to C. That is how the superposition principle works. Now, till now, the size of the charge distribution was never important to us. We introduce now the concept of continuous charge distribution. So when does the concept of continuous charge distribution come up? When the size of the charge distribution becomes important. We are now coming from microscopic to the macroscopic level. We leave the concept of quantization now. So what we say is, the concept of quantization of charge holds only at microscopic level. when the size of the charge distribution becomes important and the magnitude of the charge becomes large, then the concept of continuous charge distribution is used. So when will it be used? When size of the charge distribution becomes important, and secondly, the magnitude of the charge has become larger. Now, what are the different types of the charge distributions? So we can think line charge distribution, surface charge distribution, and volume charge distribution. Now, to describe these charge distribution, we require the concept of line charge density, surface charge density, and volume charge density. When we are using these words, they ignore the concept of quantization of charge and discontinuity in charge distribution at microscopic level. Because when we have point charges, there were intermittent spaces which did not make the system continuous. So at this macroscopic level, what are we supposed to do? We are supposed to ignore the concept of quantization of a charge. Quantization of charge has to be ignored. And secondly, at microscopic level, there were certain discontinuities in the charge distribution. They need to be ignored. At microscopic level, charge distribution is discontinuous because their discrete charges separated by intervening space where there is no charge. That is why at microscopic level we consider the charge distributions to be discontinuous. This concept of discontinuity goes when we choose larger systems of charge distribution like line charge distribution, surface charge distribution, and the volume charge distribution. Let us first pick up line charge distribution. How do we define a line charge distribution? When the charge is uniformly distributed along the length of a conductor, then it is called line charge distribution. So here we have a line charge distribution here. What we do, we divide the entire length into small segments of length dl. So one delta L, such a delta L is present here at this point O. Now this element of length would have some charge, let us call it as delta Q. Now P is a point at a distance r. How do we define line charge distribution? The line charge distribution would always be defined in terms of a quantity called line charge density, and that is total charge on element dl divided by the length of element dl. And what does delta L represent? A small length of element. And what does delta Q represent? Charge on the element of length dl. And how do we define line charge density? We represent by lambda, and that is delta Q by delta L. The line charge density is ignoring the quantization of charge and discontinuity in the charge distribution. Remember, and remember very strongly, that at the macroscopic level we are supposed to ignore the quantization of charge and discontinuities in the charge distribution. Here lambda represents microscopic line charge density, which is a smoothed out average of microscopic charge densities in the length delta L. Remember, delta L is microscopically large but macroscopically small. Line charge density lambda is nothing but charge per unit length. If I need to calculate, because I said lambda as delta Q by delta L, so delta Q can be written as lambda times delta L. If I need total charge, I must integrate delta Q, and that must be integration lambda times delta L. So that is here, and that gives me the total charge. What can be the unit of lambda? Unit of lambda can be coulomb per meter. And what are the dimensions? L power -1, T power 1, ampere power 1. How do we calculate the electric field due to this line charge? That can be calculated as E is equal to KQ upon R square. And the total charge is given by integration lambda times delta L. Similarly, in 2 dimensions we have surface charge distribution. It's a 2-dimensional charge distribution. We consider a very sheet of charge. We divide it into small area elements delta S. Again we have a point P. at a distance r from the origin O. So how do we define a surface charge distribution? When the charge is uniformly distributed along the surface area, then it is called as surface charge distribution. Delta S is small element of area and delta Q is charge on this element of area delta S. Once again, how do I define surface charge density? It is defined as total charge upon the total area. Earlier it was total charge upon total length, and now it is charge per unit area. Once again, I can say surface charge density is defined as the charge per unit area. How do we calculate total charge? It would be once again by the surface integration delta Q, and it would be surface integration sigma times delta S. What would be the unit of sigma? It would be coulomb per meter square. And what are the dimensions? L power minus 2 T power 1 ampere power 1. How do we calculate electric field at point P? It is K times the total charge upon R square. So K, total charge given by surface integration sigma dot delta S divided by R square. Once again, you can remember the surface charge density is ignoring the quantization of charge and discontinuities in the charge distribution present at the microscopic level. Sigma also represents macroscopic surface charge density, which is nothing but a smoothed out average of microscopic charge density in an area element delta S. So it's nothing but average microscopic charge density. The three-dimensional charge distribution is known as the volume charge distribution. We take a spherical surface and consider small volume elements delta V carrying a charge delta Q. We need to calculate what would be the electric field at point P due to small elemental charge delta Q. Here delta V is nothing but a small element of volume, and delta Q charge on this element of volume delta V. So volume charge density rho would be defined as total charge upon total volume. It is defined as charge per unit volume. Total charge can be calculated once again by integration delta Q over entire volume. This would be integration rho times delta V. So same concept, same way of working. What are the units of rho? Coulomb per meter cube. What are the dimensions? L power minus 3 T power 1 ampere power 1. Electric field at point P would be given by K total charge upon R square. So all fields calculated the same way. Now once again I can say the charge density rho also represents macroscopic volume charge density, which is nothing but a smoothed out average of microscopic charge density in small area elements delta V. Here also we are ignoring the concept of quantization at the macroscopic level, and we are ignoring the discontinuities present at the microscopic level of charges. So thank you students. Once again, your request is to subscribe my channel for receiving continuous updates. Thank you.